Hello, I am Hunter Unkelbauer, and welcome to my presentation on the Jordan-Holder theorem. So, just a little background before we get started, because we haven't quite reached all the definitions we need, because we haven't gotten that far in the book yet. And it's important for you guys to know what I'm talking about before I go rambling on and start confusing you. So first off, the most important thing is we want to define what a composition series is. So, what is a composition series? Well, a composition series is a subnormal series of finite length that allows a subgroup to be or a group to be broken up into simpler pieces, much like a subgroup lattice. Now, there's an important thing between a subgroup lattice and a composition series. One is that it's a subnormal series, which means that every subgroup on it is normal, which allows us to talk about normal series, which are well defined. Which is more important, there are a lot of theorems relating to that, which helps us break it down into something simpler, as well as that it must be a series of finite length. Now, why that's important is we're trying to break up a big group into something simpler. And if we break up a big group into something really big, gross, infinite, we can't really talk much about that because, it's infinite. There's not much we can say. It's just this big mess of groups that go on forever. And we don't have many properties to talk about infinite subgroups. So now there's a lot to take in. So let's have an example just to show you what I mean. So I'm sure we're all familiar with dihedral group 4 now. You know what that equals. I have it on the screen if you want to read it. Now, we know that there are two normal subgroups to D4. One of these is the cyclic group R, which is also equivalent to cyclic group 4, and dihedral group 2. This is because both of those have index 2 in D4. Now, both of those have the same normal subgroup since it has index 2 in both C4 and D2, and that is the subgroup C2. Now, C2 doesn't have any normal subgroups, so from there we just go to the identity because that's a normal subgroup of any group. So this means that there are two composition series for the dihedral group 4. That is, E is subnormal to C2, is subnormal to C4, is subnormal to D4. And E is subnormal to C2, subnormal to D2, subnormal to D4. So, just a little bit more background before we get to the actual theorem. Composition series allows us to talk about extensions of groups. These are when we have K normal to G, and G divided by K is congruent to H. Now, basically what this means is if we have a really big group, let's call it H, we know it's congruent to two smaller groups, such as G and K, which allows us to talk more about H, since instead of H being this big group that we know nothing about, we have G and K, which are probably simpler groups that we have defined properties, and multiplying them together allows us to talk more about the properties of H, which is a good thing, which allows us to break up, once again, bigger groups, smaller groups. You'll be hearing that a lot. Next, we have theorem 9.1.2. Once again, something that just allows us to get a big mess of a group into very simple terms that are well defined. Now, theorem 9.1.2 states, let G be a group and let K be normal in G. Then G has a composition series if and only if both K and G divided by K have composition series. Moreover, in this case, length of G equals length of K plus length of G divided by K. 2, the composition factors of G are exactly those of K and G times K. And 3, G has a composition series containing K. So as you can see, this allows us to break up a group such as G, which may be very big and something we may not know a lot about, into something of K and G divided by K. Then we can talk about the length of G better, even if we know nothing about it. But if we know something about K and G divided by K. It allows us to talk about the composition factors of G, which is really important because that allows us to break it up into a composition series, which is once again really important because it gives us a subnormal series of finite length, which allows us to study the group a lot more closely. And also G has a composition series containing K, which allows us to break up once again G into a composition series, and we know something about its composition series, which is important for studying G if it's a really big, really gross group. Now, onto the meat of this and the important bit, we want to talk about the Jordan-Holder theorem. Now, this theorem states that if a group has a composition series, any two composition series are equivalent. Now, going back to my dihedral 4 group example, this means that our E normal to C2, normal to C4, normal to D4 is equivalent to our E normal to C2, normal to C4, normal to D4. Now, this is important because it allows us to talk about things such as composition length. Like, once again, D4, it would have composition length of 4, since it is a series of length 4. And once again, it also allows us to talk about composition factors, the groups, the subnormal groups that make up our bigger group. And these are important because it allows us to more definitely talk about really big, really gross groups in simpler terms, talk a little bit more about the definitions, and allows us to study them a little more closely. It also means we don't have to worry about finding all possible composition series. As you know, we had to find 2 composition series for D4, but this theorem says, oh, don't worry about that, just find one and you'll be good because they're all equivalent. This is really important because let's say we had a really, really big group that's really, really ugly, such as, one, say it had 10,000 subgroups that were all subnormal to each other, series length of 10,000, and they had 15 ways to do this. We don't want to find all those 15 groups or 15 series length 10,000. In this case, we can just do one, and they're all going to be equivalent, which allows us to talk about those very big groups that may be impossible for even a computer to solve in finite terms that are more important, because then we just have to worry about one series rather than a whole slew of really gross series. Now, where can this be used? Well, it can be used to prove extensions of groups, since G divided by K is similar to a composition series, and we know if G divided by K is congruent to H, any G and any K are going to be equivalent, so that way we know that the extension is unique, and that we can talk about H in more definite terms. Once again, this also allows us to prove theorem 9.1.2, which you saw earlier, which is very useful in breaking up and splitting up very large, complex groups. As I said earlier, once again, how we can talk about its length in terms of known groups, we can talk about its composition in terms of known groups, and we can talk about its composition in terms of one of those groups, which is really important for solving those really big, really gross groups. Now, this also allows us to define a solvable group, which are just composition series equal to the identity series. Now, why this is nice is there are a lot of theorems that only work for solvable groups, and they're very nice that allow us to study these groups and solve them a lot easier, learn about their properties a lot easier. And if we didn't have solvable groups, we wouldn't be able to talk about them because we can't generalize a lot of these theorems to any group. So if you can break something down into a solvable group, or if you can figure out something is a solvable group, it allows us to use all of these theorems, which are a lot more important, and allow us to study these big, ugly groups a lot easier once again. Now, lastly, it can also be used to prove the fundamental theorem of arithmetic, which, if you don't know what that is, it basically states that any number can be broken up into a set of unique primes. Now, obviously it's the fundamental theorem of arithmetic, so we know it's important because it has that fundamental theorem. And the way it proves this is because, let's say we have a big number, like 125, and it has, 10 different ways to factor it into different primes. We know that those are all going to be equivalent, the same primes, maybe just in a different order. So, or a different, to a different power, say we have 2 to the 4th instead of 2 to the 3rd. And this allows us to prove that both those series are equivalent, which allows us to prove that they are both the same thing, which allows us to prove the factorization into primes is indeed unique. Thank you for listening to my presentation on the Jordan-Holder theorem.